Okay. So continuing with our discussion on the switching part. Before we move on, any questions have you come across, or do you want to discuss anything from our previous sessions? We can discuss now and then move ahead. If not, then we'll continue with today's agenda. Okay, fine. So, with all our understanding about unicast, broadcast, and how switch forwards data, etc., let's try to understand a particular scenario in a network. And this scenario is specifically only for uh, switches, and that also layer 2 switches. Okay. So let me draw 3 switches. Switch number 1, switch number 2, and switch number 3, right? And there are PCs connected to them, PC number 1, PC number 2, and PC number 3, right? So these switches are connected to each other, interconnected like this. PC1's MAC address is 1111, PC2's MAC address is 2222, and PC3's MAC address is 333, right? Now, again, let's go back to our scenario and let us assume the same thing where the PCs, they know about each other's MAC addresses, but the MAC address table in these switches are empty, right? So this is our assumption. So let's imagine PC1 is sending a message to PC number 3, okay? And we are concentrating only on the layer 2 part. When I say layer 2 part, we're concentrating only on the MAC addresses. So when PC1 sends a data to PC3, right? So the source MAC is going to be 1111 and destination MAC is 3333, right? And as I said, we are assuming that the MAC addresses, so not MAC addresses, MAC address table of these switches is empty, right? So for switch 1, this is the MAC table, MAC and port number. Okay, this is for switch number 1. For switch number 2 also, MAC and port number. For switch 3 as well, MAC and port number. And let me just give a interface number 1, 2, 3. Interface number 1, interface number 2, interface number 3, 1, 2, and 3. Okay. So now when PC1 sends the data to PC3, what's going to happen? We all know that the data is received by switch number 1. Switch number 1 makes an entry for the source MAC address, right? And then it checks for the destination MAC address. And when it does not find the destination MAC address, what is it going to do? It's going to broadcast, right? So it will broadcast this packet to switch number 2 and switch number 3. Not toward these switches, but out of interface number 3 and 2. It will broadcast it out of interface number 3 and 2. It will reach switch number 2 and switch number 3. Now let's concentrate in the clockwise direction first. Okay, so we'll come to the anti-clockwise direction later. And let me take a different color for anti-clockwise. Now, switch 2 receives this data, right? It will read the MAC address. It will make an entry for it, right? And it will look for the destination MAC address. It will not find the destination MAC address, and it will broadcast it out of all the interface, right? Then switch 3 will receive the same packet, right? It will make an entry 1111, right? It was received on interface number 1. Switch 3 will look for the destination MAC address. It will not find it in the MAC address table, and hence it will forward it out of all the interface or broadcast. Now, switch 1 is again receiving the same packet again. Correct? It is receiving the packet once again. But now when it has received the packet, the switch checks the source MAC address. It sees that I have a source MAC address. But now instead of receiving it on interface number 1, I am receiving it on interface number 2. So what happens here? Switch number 1 is going to update this entry. It will delete this entry. It will make a new entry saying now source MAC address 1111 can be reached through interface number 2. Okay. Now this was a clockwise direction flow. Now let's check the anti-clockwise direction flow. So before this was received by switch number 3, obviously this packet that was forwarded by switch number 1 would be received by switch number 3, right? So when switch number 3 received that packet, what would have happened? It would have made an entry saying that I am receiving a MAC address of 1111 on interface number 3, right? Then what would it do? It will check the MAC address table for the destination MAC. It will not find it. It will broadcast it out of all the interface. Right? But now, please remember, there is a clockwise direction packet is also coming. So what would switch number 3 do? Switch number 3 would basically erase this and make a new entry. Correct. Similarly, for switch number 2 also, 2 received this packet. Then when 3 forwarded this packet, it is receiving it on a different interface. So switch 2 also updates its MAC address table with the new entry. And switch number 2 will also broadcast it out of all the interface. Now what has happened? The packet is now received in the anti-clockwise direction. Now what switch 1 is going to do? It will again read the data. It will see now I am receiving the same data, but on a different interface. 1111 is now being received on interface number 3. So what is basically happening here is that the data is the same data. Okay, that is this data is being sent to all the different switches in the network or in this topology is sent across these 3 switches. But every time the packet is sent out or broadcasted out, the MAC table of these switches is not stable. They have to keep on updating. Okay, now what will happen here? Switch 3, so not switch 3. Switch 1 will receive the packet. Okay, here in the clockwise direction, it receives the packet, it makes an entry. It does not see the destination MAC in its MAC address table. Now what is it going to do? It's going to forward it out of all the interface. So what is going to happen is every time the data is either received in the clockwise direction or in the anti-clockwise direction, the MAC address table of switch number 1 keeps on updating. First, it will say 1111 was received on 3. No. Then what will happen? The data is received on the other interface. It will erase this. It will make a new entry. Then it will receive on interface number 3. It will erase this, make a new entry. Like this, it will keep on happening. Not just with switch 1, even with switch 2 and switch 3. Every time the data is received on a different interface, they have to update the MAC address table. Okay. And this is what you call it as loop in the network. Okay, this is what you call as looping of data in the network. So your data is actually, without going to the destination, it is continuously circulating in the network. And because of this circulation, what is happening? The MAC address table of the switches is not constant. It keeps on updating. Right, every time the same data is received on a different interface, it has to update the MAC address table. Now you may think PC3 receives the data. Okay, PC3 will receive the data. Okay, let's say PC3 receives this data. It is sent. Okay, PC switch 1 makes an entry for interface number 1. PC he makes an entry for switch 3 also makes an entry. Switch number 3 forwards data. PC3 receives this data. It will send back. Okay, when it sends back, it makes an entry. Switch number 3. Okay, now by the time switch number 3 forwards this data, what would have happened? This data from over here would have been received. So what would happen? Automatically, this interface would be updated as interface number 1. Now, instead of forwarding the data back to switch number 2, back to switch number 1, it will forward it over here. And by the time this data, the data that is sent by PC number 3 is received by switch 1, switch 1's MAC address table, original MAC address table is completely removed. So switch number 1 will always see 1111 being received on interface number 2 or 1111 being received on interface number 3, never on interface number 1. So what is happening? Even the reply that is being sent by that PC is also getting looped in the network. The original data is also looping, and the response that is being sent by that PC is also looping, because the update that has happened on the switch is so quick that the original update is no more present in the MAC address table. So what is happening here? Your data is continuously circulated in the network, right? Any problem understanding this scenario? No? Okay. Now, because of this, what is happening? Basically, we just saw what is a loop. Loop in layer 2 network. Right? Loop. Now, because of a loop, what is happening? First, duplicate entries. Okay. Duplicate entries of the same data. Duplicate entries of the same data is in the network, right? Second, overload on the switch. Overload on the switch. Now, what is overload on the switch? Meaning that every time a data is received by the switch needs to process it. Okay, the switch needs to process it. And over here, it's just not one single data. Okay, one data was multiplied into 2. Right, here again it is multiplied into 2. Here again it is multiplied into 2. This same data is received by the switch. Again it is multiplied by 2. Right, now the return data also, this the data that PC3 sends, it also gets circulated. Right, so what is happening? The processing or the CPU utilization of the switch increases, which we call it as overload. It is an overload of the switch. When it is an overload of the switch, what would eventually happen? Processing of data would slow down, is low. Okay, because there are so many packets that the switch needs to read and make a forwarding decision. So what would happen? Basically, the utilization or the RAM processing of the switch increases, thereby slowing down its forwarding capability. Right, that is what you call it as processing data is slow. Then third, your MAC table, right? MAC table is not stable. MAC table is not stable, right? So every time a new data is received, the MAC table of the switch gets updated with a new entry. So you do not have a proper stable table, right? This is what would happen when you have a loop in the network. And in short, this is what you call it as a broadcast storm. broadcast storm. So in the interview, they may ask, what is a broadcast storm in a layer 2 network? Or just they may simply just ask you, what is a broadcast storm? So first of all, you need to understand broadcast storm is a broadcast storm. Because of these three things, you will see a broadcast storm in the layer 2 network. Now, what is a broadcast storm? Broadcast storm is a phenomenon when you have a loop in the network. When you have a loop in the network, you will see duplicate entries of the same data that is circulating in the layer 2 network, because of which what would happen, there will be an overload on the switch, and thereby the processing of data would be reduced by the switches. Okay, and because there is an overload on the switch and there are duplicate entries of the same data in the network, the MAC table of those switches is never stable. This is what a broadcast storm is. And why does a broadcast storm happen? It happens because of the loop in the network. Okay. Now, if someone asks you, what is a loop in layer 2 network? You don't have to explain all this. You don't have to explain all this. Okay. Now, think of me as an interviewer. Now, okay, before I ask you this question, any problem understanding what is a broadcast storm and whatever we saw right now? Any doubts? Anyone?
No.
I have one doubt, okay?
Yeah, Vivek.
Lakshay sir. So as you are telling that whenever it broadcast happen, okay, in this scenario, so the switch will continuously update its MAC, right?
Yeah.
So switch can means whenever they will get new information on their interface, so they will reset the MAC address R table on the switch entry.
Yes. So
Okay. Mm-hmm.
if the switch is receiving the same MAC address, okay, the same MAC address in a newer update, it will erase the old entry.
Okay.
Okay.
There is no any kind of sorry.
So what is happening? The first time switch number 1 received the data, it received it on interface number 1. Correct. Now what happened? It came back like this. So what is happening? The switch 1 is reading. We know that switch always reads the source MAC address. Whenever a data is received, the switch will read the source MAC address. This is one of the basic function of the switch. It will always read the source MAC address. Now here what is happening? It is receiving the same source MAC address, but it is receiving on a different interface. So it will erase the old entry and make a new entry. Clear?
Yes, sir.
Okay. Do you want to ask anything else? I think I stopped you midway.
नो नो भूल गया मैं ठीक है रिकॉर्डिंग डिवाइस करके कल या परसों पूछ लूंगा नो इशू
Okay, fine. As I was saying, you don't have to explain. If someone asks you in an interview, now think of me as an interviewer. I am asking you, now you know what is a loop, what is a broadcast stop, right? Now if I ask you what is a loop in a layer 2 network, tell me in a very simplest form, tell me in a very simple form. I do not want a detailed explanation like, what is a broadcast storm, you will see duplicate entries, overload, etc., etc. In a very simple form, tell me what is a loop in layer 2 network. Just give a try.
It creates MAC address instability in the network.
But that is not the definition of a loop, right?
Right.
MAC table instability is because of a loop. But that is, but what is a loop? Okay, or in a general English term, what is a loop? Not from a networking point of view. What is the meaning of, what is the definition of loop? If you just open up a dictionary, what you may find? What's the definition of a loop?
You
Okay,
can say
Like
jam.
same data we receive. Like
yeah. Okay, you use send and you receive the same data. Yeah.
same
Someone
data.
else.
Yes.
Yeah. Someone was saying anything. That Vivek or Mohit was saying anything. विवेक कुछ बोल
नो
रहे थे?
आई वाज जस्ट सेइंग, मैं कह रहा था कि जाम जैसा हो सकता है, जाम बोलते हैं ना, रोड पे जैसा जाम हो
ओके,
जाता है
कंजेशन.
ऐसा. हाँ, कंजेशन.
Congestion. All right. Okay. Again, uh, yeah, this gives a like not a perfect answer. Okay, congestion is definitely not the definition for a loop. Okay, if we check in the dictionary what is a loop, probably obviously different dictionaries will have a different way of explaining it, but something is like the start of a point is equal to the end. At where you start, you end there itself, or basically going in circles. Right? This is what you call it as a loop. Now, after you have understood this whole broadcast storm and a layer 2 loop in the network, if an interviewer asks you what is a loop, the simplest and the best explanation to an interviewer with this definition is what I find, is what I feel. If a MAC address, okay, if a MAC address is received on two different interfaces, it is a loop. Very simple definition. And if the interviewer is very knowledgeable person and if he is not, if he is also technically good and if he understands your statement, he'll appreciate it. Because whenever someone asks you a loop, or whenever have asked someone a loop, they give me all this, because of loop this happened, this happened, this happened. You're giving me the after effects of loop, right? I'm not asking you the after effects of loop. I'm asking you what is a loop, right? So the best answer for this is when you receive a single MAC address on two different interfaces of a switch, it is a loop. So here again, let me explain you this definition. Switch 1 receives the MAC address on which interface? Interface number 1. Then it goes over here and comes back to switch number 1. Now switch number 1 is receiving the same MAC address on a different interface. This is what I explained just now. When you receive the same MAC address on two different interfaces of a switch, it is a loop. Simple explanation. Okay, any problem understanding that statement? Anyone? Okay, now since we have understood what is a loop, what is a what is a broadcast storm, etc. Okay, what can be done to avoid this loop? Okay, we all know that in a layer 2 switch, as not layer 2 switch, in a layer 2 environment, okay, to avoid a loop, what basically can be done is to remove one of the interfaces. Right? When you remove one of the interface, okay, now what is going to happen? Switch 1 will receive the data, okay, it will make an entry and it will broadcast it. Switch 2 will receive the data, it will make an entry and it will broadcast. Switch 3 will also receive the data, it will make an entry and it will broadcast. Because this interface is not present, the data between switch 2 and switch 3 did not go through. And that is why we were able to avoid the whole loop in the layer 2 network. Okay, so to avoid a loop, you basically remove or basically disable a particular interface so that a loop is avoided. But in real time, okay, but in real time, the layer 2 switch connectivity is not as simple as what you see in the topology. It is very complex. You have 50 or 100 switches connected together. Okay, you may see interconnectivity. Okay, and going there and physically disabling or going into the switch and going onto the interface and doing a shutdown is not a viable solution. It is a tedious task, right? Let's imagine I'm for the drawing purpose, I'm just drawing them as a circle. Okay, imagine you have many switches. Okay, consider them as switches. I know switches are drawn as squares or rectangle, but for faster drawing purpose, I'm drawing them as circles. Okay. Imagine you have connectivity. Okay, interconnectivities are there. Okay, like this, something like that. Okay, again, it's a hypothetical drawing, right? Now, in such a complex network, you want to create a topology where there is no loop in the network. It is not possible. It is possible, but it is a very time-taking task. Right? It is a very time-taking task. You cannot go into each and every switches CLI, do a shutdown of the interface so that the interface is no more sending or receiving a traffic. So human error is high. The chances of human error is extremely high. Okay, so Mohit, you do not need a diagram to explain in the interview. However, if you if they are asking to draw a diagram and explain, it's good. You can draw the diagram and explain. If not, at least draw, as I said, have a paper and pen with you. Draw the diagram on your paper. Okay, draw the diagram on your paper and then start explaining. So that, as I said, your thought process is clear. Okay, your thought process is very clear. So so it is always best to have a visual explanation with you. Okay, coming back, manually disabling all these interfaces and shutting them down will have a lot of human error. Why? Because we may disable some important interface where there is a lot of traffic. We do not want that. Okay, so human chances of human error is more. And in such a scenario where there are 50 switches, 100 switches, 150 switches connected together in a data center environment, like a data center environment, you do not want human intervention. You want everything to happen automatically, right? Where in such a scenario, these switches will talk to each other and automatically create a loop-free environment. Okay, what is a loop-free environment? Where there is no loop. So here, if I remove this interface between 2 and 3, this is what your loop-free environment looks like. So in a complex network where I do not want human error and I want the devices to take their own decision and create a loop-free environment, we created a protocol called as spanning tree protocol. Okay, the purpose of the spanning tree protocol was to automatically create a loop-free environment. Okay, on its own, without any human intervention. Right. So that is what is spanning tree protocol used for. Okay. Now, spanning tree protocol. Now let's get into the discussion of spanning tree protocol. I know you guys may be already aware of spanning tree protocol. However, let me just explain. So Spanning tree protocol, we know that it is called as 802.1D. The IEEE name is 802.1D. Right? That's the IEEE name for spanning tree protocol. And why is it used? It's used to create a loop-free environment. Right? It is used to create a loop-free environment. Now, with the name tree in the protocol, spanning tree protocol, imagine a tree. We know that, right? You know, a tree looks basically like this. I'm just drawing a rough diagram, right? It has branches, right? And it has leaves also, right? So in a tree, we know that the roots are the most important part of the tree, because roots act like a nervous system of the tree. Through roots only all the information is passed on in the tree. Similarly, our human brain. I'm just drawing a rough diagram of a human brain from the side. Okay, it's a rough diagram. Okay, and you have a spinal cord. Right? We know that the brain is connected to spinal cord, and this spinal cord is connected to millions of nerves, right, which are connected to spinal cord, and those nerves go through and connect to different parts of our body, right? So basically, the brain in our nervous system is the root. Through the root, the brain basically sends us information. Okay, basically it sends a message that goes through the spinal cord, through the nervous system, and to the body part, right? And the body reacts based on that, right? And we know that how quickly it does it, right? There is nothing faster than the message that is flowing through our body. Even light does not travel that fast. That the neurological messages, or the neuron speed that the brain and the our body, they communicate, is extremely fast, faster than light. Anyway, coming back to our discussion, root, the brain is the root for it. Similarly, for a spanning tree protocol, and because there is a tree involved, there should be something which will act as a root, and that root in the spanning tree protocol will be the main controller of your whole spanning tree environment, and it will be responsible to create a loop free environment. Okay, again, just like roots in the tree, just like the brain in our body, there is also a root in the spanning tree protocol, which will help to create a loop free environment and control the layer 2 network. Okay, and as the name goes, right, we have already discussed, that thing is called as a root switch. It is called as a root switch. Okay, so the root switch is basically responsible to create the loop free environment. Okay, because of the root switch, because of where the root switch is in the what in the layer 2 network, all your other switches will behave and create a loop free environment. Okay, so as we know that in a real time scenario, there are a lot of switches in the network. How will you choose which switch will become the root switch? Which switch will become the root switch? So a root switch, first of all, is elected. Election happens of a root switch. Again, these are the questions. How is a root switch elected? Okay, so election happens of a root switch based on few criteria. So what is that criteria? First, the spanning tree priority. Spanning tree priority of the root switch is the lowest. Whichever switch in the network has the lowest spanning tree priority will become the root switch. Now the spanning tree priority starts from, it goes from 0 to 65535. Okay, and the priority by default is 32768. Okay, 32768. 65535 32768. Okay, this is the default priority. So all these switches in the network will have a default priority of 32768. And I'm talking from a Cisco device perspective. In Cisco switches, it can be a layer 3 switch, it can be a layer 2 switch. Spanning tree is enabled by default, and all these switches have a default priority of 32768. I'm not sure of other vendors, but in Cisco switches, the spanning tree is enabled by default on the switches. So if you connect different switches together, the spanning tree will run automatically between these switches. You don't have to do anything. Okay. So spanning tree is enabled by default on Cisco switches with the default priority of 32768. Now, my question, no one has asked me this question, but I am asking you this question. Why is the default priority of the spanning tree 32768? Why? Why is 32768? Why cannot it be any other number between 0 to 65535? Why is it 32768?
I heard somewhere that there is some like a square something is there. That's why. If you 0 to 4096, I don't know exactly, 2 raised to something or some ratio is there. So if we add 0 to 4096, this kind of a number will come. अभी एग्जैक्टली याद नहीं आ रहा कहाँ पे, तो देखा था मैंने इस कहाँ पे अभी याद नहीं।
Okay. So okay, coming to this question, we'll continue about root switch and things later. But why is it 32768? Now, okay, the priority, okay, priority of spanning tree protocol is a combination of what do you say? Yeah, system extension number, called as a system extension number, plus your VLAN ID. That is your priority in spanning tree protocol. Okay, system extension number plus your VLAN ID. Okay, yeah. Now this system extension ID is also called as a priority. It is also called as priority plus VLAN ID. Okay, this basically, okay, this is what you call it as system extension. Sorry. Okay, let me rephrase again. Your priority of spanning tree protocol is basically your priority plus your VLAN ID. Together, this in spanning tree protocol, we call it as system extension number. Okay, system extension number. So your priority is basically a 4-bit number plus your VLAN ID is your 12-bit VLAN ID. Okay, so in total, your system extension number is a 16-bit value. So your priority is a 16-bit value. And your priority is determined by a 4-bit priority number plus your 12-bit VLAN ID. Together, it is a 16-bit value, which we call it as a system extension number. Okay, now 16-bit. Okay, please listen to this very carefully. If you want to answer, why is it 32768? Why not something else? Let's listen to this very, very carefully. Okay, so let's write that 16-bit together because it's a priority plus your VLAN ID, right? So your VLAN ID is 12-bit and your priority is 4 bits, right? So let's write down these 4 bits first. 0 0 0 0, right? Then 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Yeah. Okay, so this is a 4-bit priority number. Now add these VLAN IDs, that is a 12-bit VLAN ID in front of them. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Sorry, why did I go beyond 12? Sorry. What was I counting? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So 12-bit VLAN ID. I'm not going to write down everything. Okay. So just imagine you have a 12-bit VLAN ID. Now you are basically writing this together. I have separated it with a space, but the computer does not read the space, not the computer. The switches processing does not read the space in between. I have written the space just to show you the difference over there. Now, what is the value of this first number? It is 0, right? Because there is no 1 over here. Correct? There is no 1 over here, right? Now let's write again those zeros. Right. Now what is the value of this number? So if you count 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is 2 power 12. 2 power 12 is basically your 4096. Then it is 2 power 13. 2 power 13 is 8, 6 plus 6, 12, 1 and plus
8192.
8192. Right. Then what is happening? 2 power 12 plus 2 power 13. You need to add these two. That is why, okay, so if you write down all these numbers, in the end, this number 1111 you will get is 65534. No, sorry, 65535. So starting from 0 up till 65535. You can have these priority numbers. Okay, any question understanding the priority numbers? Why is it 0 starting from 0 up till 65535? Any problem understanding this part? Mohit, Vivek?
No, sir.
No. Okay. Now the mid value over here, this y, 0 1 1 1. Okay, so you have in total you have 16. So the eighth, I think it is 8th or 7th. I'm not sure if it is 7. Okay, let me quickly open up. Yeah, okay. This one. So this guy over here, okay, 1000 and all zeros, 1000 all zeros. This is in between 0 and 65535, and that value is 32768. That is why the priority is not chosen in any random way. It is chosen as the mid number between 0 and 6553. And this is the logic. And if you are already aware of spanning tree protocol, we always decrease the priority or increase the priority of a spanning tree switch in the multiples of 4096. Correct? Has any one of you have heard it? We always increase the priority of the spanning tree protocol in the multiples of 4096. Now you also know the reason why. Because 0 plus 4096 plus 4096 8192 plus 4096 is some number plus 4096 is some number plus 4096 plus 4096 plus 4096 32768. Then you keep on adding 4096 and you will eventually reach 65535. Similarly, you decrement the value minus 4096 minus 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 minus. Eventually, you will reach 32768 minus 4096 some value minus 4096 8192 minus 4096 is 4096 minus 4096 is 0. This is how you calculate the value of spanning tree protocol. Okay, so with this, we saw two interview questions. Why is the default priority 32768? Then why is the priority of a spanning tree protocol incremented or decremented in 4096? Now you know the reason. So as I said, now we have considered, okay, we know that, and now I've been talking like this is a VLAN ID. These 12-bit is a VLAN ID. Now we know that there can be no VLAN 0, right? There can be no VLAN 0, correct? So if you are, if you check on a switch, the priority for VLAN number 1, okay, all you need to do is change this value to 1. Okay, so what will happen? 4096 plus 1, and you will see the system extension as 4097. If it is VLAN number 2, you will see 4096 plus 2, 4098, like that. If you're keeping the priority as 4096 and you add any VLAN to the spanning tree protocol, it will increment the VLAN number to this value. So if your default, if you have seen, the default value is 32768, right? 32768. Now 32768, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now 32768 is the default VLAN. Now you're running spanning tree protocol for VLAN number 1. So what is going to happen? This will become 1, and we know that it is a addition of this priority as well as the VLAN ID. So 32768 plus 1, your system extension ID is 32769. So if you're keeping the default priority on all the switches and you keep on adding different VLANs, for different VLANs, the spanning tree priority will change, meaning that to the default priority of 32768, that VLAN number gets added to the priority. So let's say you're running VLAN number 10. So 1010 will be the VLAN number over here. So 32768 plus the VLAN ID gives you 32778. This is your system extension ID with the default priority and for VLAN number 10. Okay, any question? Mohit, Srinivas, Vikas, sorry, Vivek.
No, sir.
No, I understood. Okay. So coming back to our discussion of the root switch. So the root switch is elected. I'm writing in short. Root switch is elected based on the lowest priority. Okay. And the default priority, we know that it is 32,768. This is the default value. Now, if all the switches have a default priority value of 32,768, then which switch would be chosen as the root switch? Because it's going to be a tie. All the switches, if they say my priority is 32,768, no one has a lower priority, right? Which switch then will become the root switch? So when you have a tie for a priority, the second criteria to choose the root switch is whichever switch in the network have a lowest MAC address, that switch becomes the root switch, and this is the final decision, because we know that MAC addresses is unique in nature and none of the switches will have a same MAC address. So whichever switch in the network has a lower MAC, it will become the root switch. Okay, and how is a lower MAC considered? So over here, let's go back to our diagram. Between switch 1, 2, and 3, we just assume MAC address is 111.1.222.333, right? So obviously, in this particular topology, switch 1 becomes the root switch, correct? Now, again, in real time, you will not see 111.222.333, correct? So there, how are you going to decide which MAC address is a lower MAC address? So let me just show you how to find that out. Okay, so here, if you see, you have two MAC addresses, 70 B6 4F 6E A3 46 4F A4 75 07 2E 6P. These two are real MAC addresses. Okay, now if we have to find out which is the lower MAC address, how will you find out? Can someone just give a wild guess which will be the lower MAC address out of these two? Just a guess.
Second one.
Second one is a lower MAC address.
Like compared last 4 digits. Last 4.
Okay.
If it is from the first means, it will be like 7, which is 7 is lower. But last 4 digits only will compare, right?
Okay, so here, let's check which is a lower MAC address. So whenever a switch is comparing the MAC addresses, it will always compare from left to right. It is always compare from left to right. Okay, and it also compares left to right, digit by digit. Digit by digit. Okay, so when the switch is comparing these two MAC addresses, it will compare 7 first, 70 B6. I'm just writing these 4 values over here. Then F4 A4 75. So as I said, it will compare digit by digit from left to right. Okay, and out of these two, whichever is a lower, meaning that it compares digit by digit. So first it compares 7 and F. And please remember, these are hexadecimal value. Obviously, 7 is lower than F. F is 15. 7 is 7. F is 15. Correct. So obviously 7 is lower than 15 and this MAC address is lower. The switch will not compare the other part or the other digits in the MAC address. It will compare left to right, digit by digit, and whichever whichever match happens or whichever MAC address is or whichever digit is lower, it chooses that particular MAC address as a lower MAC address. So now let's assume instead of 4F here, it was again 70. Let's say it is 70 here. So it will compare 7, 7, it is same, move on. 0, 0, it is same, move on. Then B and A. Out of B and A is a lower MAC address. A is a lower number. And hence this whole MAC address will become a lower MAC address for this switch. Clear? Any question? How switches compare MAC addresses?
No, sir.
Okay, thanks. Now, so let's go back to our diagram. Okay, let me remove the PCs and just simply drawing the switches over here. Okay, assuming PC switch 1's MAC address is 1111, switch 2's MAC address is 2222, switch 3's MAC address is 3333. Right. So between these three switches, switch 1 will become the root switch. That's the first process that a spanning tree does between these switches. Elect the root switch. So election of root switch happens based on two criteria. First, the lowest priority, which is the default 32768. If 32768 is the default, they move on to the lowest MAC address. Whichever switch has a lower MAC address, it becomes the root switch. So in this topology, switch 1 has a lower MAC address, and that is why it has become the root switch, assuming that all the three switches have the default priority of 32768. Okay. Then, after the root switch is elected, what happens? On the non-root switches, so which are the non-root switches? 2 and 3. They are non-root switches. Switch 1 is a root switch, so obviously 2 and 3 are the non-root switches. So on the non-root switch, what happens? Elect a, so instead of this, let me write. Yeah, okay. Second, on the non-root switches, elect a root port. Elect a root port. Okay. Now, what is a root port? Root port is a port through which, please listen to this very carefully. They may ask you these interview questions for spanning tree. What is a root port? Explain what is a root port. So root port is a port through which a non-root switch will send data towards the root switch. Okay, listen to this again carefully. Root port is a port through which a non-root switch, switch 2 is a non-root switch, will send data towards a root port. Okay. So for switch 2, there are 2 root ports. Similarly, for switch 3, there are 2 root ports. It can send data to the root switch like this and also like this. Okay. So the root port is a port through which a non-root switch will send data towards root switch. However, there can be only one root port. That's the condition. There can be only one root port. Okay, one root port. So Here you have switch number 1, switch number 2, and switch number 3. The root switch is switch number 1. These two are non-root switches, switch 2 and switch 3. So switch 2 also has 2 root ports, right? It can reach the root switch via this and this interface. Similarly, 3 can reach the root switch directly, and it can reach the root switch like this, right? But the second condition says only one root port can be there on a switch. Only one root port can be there on the switch. So between switch 2, which interface? Let me write that down. One interface, first interface, second interface, first interface, second interface. This is first interface, second interface. Okay. Out of interface number 1 and 2 on both these switches, both the non-root switches, that is switch number 2 and switch number 3, which will become the root. Okay. So the election criteria is lowest cost or lowest spanning tree cost to the root switch. Whichever interface has a lower spanning tree cost to reach the root switch, it becomes the root port. And this is per switch basis. It happens on each switch. Okay. So on each switch, on each non-root switch, a root port is elected. And if you have more than one root port, whichever port has a lower spanning tree cost to reach the root switch, it becomes the root port. Now, what is this cost? Okay, think of a very similar way, like, lowest distance to reach a particular destination, right? So when you, let's say, let's say from Delhi to Bombay. Okay, from Delhi to Bombay, I want to take a road trip, right? So when I on Google Map, when I do a Delhi to Bombay, it shows me different paths, right? It shows me multiple ways to reach Bombay. However, it gives me it shows the path as blue, which has a lowest distance as well as has a lower time, or it has the lowest time to reach that destination. That is chosen as the best path. Similarly, the switch, whichever has a lowest cost to reach the destination or the root switch, will be chosen as the root port. Now, what is this cost? Now, spanning tree already has a default cost defined. Okay. So if you see here, you have this spanning tree cost. Okay. Forget the second column. Just consider it on the forget the third column. Consider it on the first column. Right? So you can see these costs, spanning tree costs, are already defined by the spanning tree designers. Whoever created the spanning tree protocol, they have already defined this. Now, this spanning tree cost is defined based on the interface that you're using. You can see there are different types of interfaces based on the interface speed. 10 Mbps, 100 Mbps, 1 Gbps, 10 Gbps, your spanning tree cost is decided. Lower cost, higher spanning tree, lower speed, higher spanning tree cost. So you can see the lowest is 10 Mbps and it has a cost of 100, right? And if you come down to 20 Gbps, it has a better speed and it has a lower cost of 1. So as your speed increases, your spanning tree cost also decreases, right? So basically it's like speed and time. If you have lower speed, more time to reach the destination. If your speed is more, you will take less time to reach the destination. It's a similar thing. Okay. Now, For understanding purpose, I'm assuming the cost is 1 for all the interfaces in this topology. The interface spanning tree cost is 1. So I'm just writing that down in green. Interface cost 1, interface cost 1, 1, 1. Even for the root switch, the interface cost is 1. Meaning that the interface's speed is 20 Gbps. Okay, that's the interface speed. So I'm just writing down the cost over here. Now for switch number 2, it has two ways to reach the root switch. One is this way, one is this way, which has a lower cost. Obviously, from switch 2 to switch 1, the cost is going to be 1. Switch 2, switch 3, switch 1, the cost is going to be 1. The outer like exit interface cost to 3, then the exit interface cost to 1. So 1 plus 1 equals 2. So via this way, the cost is 1. Via this way, the cost is 2. So obviously, switch 2 is going to prefer a lower cost interface, and that interface then becomes the root port. So this interface here is the root port. Similarly, for switch number 3 also, it will check for the root cost or the cost to reach the root switch. Obviously, this will have a cost of 1 and this way will have a cost of 2. So for switch number 3 also, this interface becomes the root port. Okay. Any question with the root port election? Okay. Now, sometimes there are scenarios where your root port cost is also same. Okay, let's imagine this situation. So now this is one of the interview questions. Okay, for switch number 4. Okay, switch number 1 is the root switch. Now I'm asking you this question. For switch number 4, which will be the root port? Assuming that the cost across the network is same. Assume the cost is 1 for all the interfaces. Now you guys tell me which interface will be the root port. Interface number 1 or interface number 2? Which will be the root port? Root port is elected based on the lowest cost to reach the root switch. Here, which will be the root port?
To reach
Any guess?
root switch, both the sides cost are same.
Yeah,
And,
in everywhere the cost is same.
like interface, based on the interface, like lowest interface, like first one. For port number 1 on the switch, it will be like the root port.
Okay. Yeah, that's a good guess. However, that's in root port election, interface number does not come into picture. Yeah, that is a good guess. I would say. Guess elected. Now, you guys want to guess? Okay. So, cost for switch number interface number 2 of switch number 4 to reach the root switch is 1 plus 1, that is 2. Right. From here also, it's 1 plus 1, it is 2. Right. So what has happened here is, for root port also there is a tie. In such a scenario, what happens is that whichever interface is connected, okay, now the root port is selected based on the neighbor's MAC address. How? Whichever neighbor has a lower MAC address. Switch 4 has two neighbors, switch number 2 and switch number 3. Out of these two switches, whichever switch has a lower MAC address, that interface becomes the root. So in this scenario, Switch 2's MAC address is lower than switch 3, and that is why this interface becomes the root port. Okay, so here, next line is if spanning tree cost is equal, okay, then lower MAC address of the neighbor wins the root port election. Okay, clear? Any doubt with the second or the last point of how a root port is elected? No doubt, no questions? Okay. Now, after a root port is elected, third, on your non-root switches. Okay, one more thing. This is a non-root switch. On your root switch, all ports. Sorry, okay, not this. Not. Okay, coming to the third point. On your non-root switches, elect a designated port. Now, there is no definition of a designated port. A designated port is a port. All ports on your non-root switches, all ports except root port are designated ports. Okay, so switch number 1, switch number 2, and switch number 3. Okay, switch 1 is the root switch. We saw this was a root port. This was a root port for switch number 3. So on your non-root switches, all ports except your root port are designated ports. So for switch 2, this is a designated port. For switch 3, this also is a designated port. Okay, this also is designated. Now, on your root switch, all ports are designated port. So for switch number 1, this is designated port. For switch number 1, this also is a designated port. Okay. I hope there is no question with designated. So all ports except your root port on this switch is a designated port. Now, what I'm explaining is a step-by-step process of how a spanning tree protocol is working. Okay. Step 1, it elects a root switch. Step 2, it elects root port on non-root switches. Step 3, it elects designated port on non-root switches. Okay. Step 4. Step 4, on your non-root switches, elect a block port. Elect block port. Okay. Now, how does a block port election happens? There's an election for a block port also. So the criteria is you can have a root port to a designated port connectivity. Okay, you can have a designated port to a block port connectivity. Block port meaning the interface is blocked. That port cannot send or receive any data. That is block port. Okay, but you cannot have a designated port and a designated port connectivity. So in our diagram over here, switch 1 is the root switch, switch 2, switch 3. This was a designated port. This was a designated port. This was a root port. This was designated, this root port. So if you see here, I said root port designated port connectivity is okay. So you can see root port designated port connectivity over here. That is okay. Okay. Second one we have not seen yet, designated port block port, but we'll see in some time. And a designated port to a designated port connectivity cannot happen because that is where you will find a loop, because of which you will always see a loop in the network. So you can see here between 2 and 3, the two devices are connected through their designated ports, and hence this connectivity should be stopped. So out of these two designated ports, one of them should be converted to a block port. One of them should be converted to a block port. Okay, either 2 will change its interface to a block port or 3. So how is that election happening? First, higher cost to the root switch. Whichever switch has a higher cost to reach the root switch will convert its designated port to block port. If that is a tie, so here you can see for switch 2 to reach root switch, the cost is 1. For switch 3 also, the cost is 1. So the cost is a tie, right? The spanning tree cost to reach the root switch is a tie. Now, what will happen here is that second criteria, if that is a tie, higher MAC address. Whichever device has a higher MAC address will convert his designated port to a block port. So here, obviously, switch 3 has a higher MAC than of switch 2. That is why switch 3 will change its interface to a block port interface. When this switch changes its interface to a block interface, your topology may look like this. And this is how your spanning tree creates a loop-free environment. Okay, any question with block port election? Okay, now let me just give you a sample scenario, random scenario. Okay. Okay, this is a topology. This is your topology. Okay, now this is your assignment. Considering that your spanning tree priority is 32,768 and the cost, spanning tree cost is also 1. These two are the assumptions. Now what you're supposed to do is create a loop-free environment. Think how spanning tree protocol will create a loop-free environment. This can be an interview question also. They may draw some random diagram, connect switches, or make some connectivity and ask you to create a loop-free environment, giving this scenario, saying that the priority is 32,768 and the interface cost is 1. All the spanning tree cost is 1. So what you're supposed to find first, which is a root switch. Second, what are the root ports on each non-root switches? Third, which are the designated ports on each non-root switches? Fourth, which are the block ports on each non-root switches? When you find all this, eventually you will be able to create a loop-free environment, or the spanning tree will be able to create a loop-free environment. So this is your assignment. Okay, or you can think of as a homework. So Monday we'll discuss this of how spanning tree will find a loop free environment. Okay. Any question with your homework? No?
No, sir.
All right.